All right, so we're on page 358. We're doing number 40 here in chapter 8. All right, so what this is asking us, this is a very mind-bending, confusing topic. Diels Alder's reactions when both reagents are unsymmetrically substituted with resonance. Dear God. So what it's asking us is, what is the major product when the methoxy substituent in the preceding reaction is bonded to C2 of the diene rather than to C1? So if we're looking at this, and they are naming it this way, it's very blurry. 1, 2, 3, 4, it's our conjugated system. They want us to move our methoxy to the group 2. So that's what I did over here. This is 1, this is 2, this is 3, this is 4. I have our methoxy here. All right, this is our conjugated diene. This is Diels Alder. If we can, we want to connect negative to positive. And deal, this guy's wheeling and dealing, wheel. We're making a cycle. We're making a cyclic compound as our end result, okay? All right, so first thing we need to look at is this conjugated diene symmetrical? No, it is not, okay? So what does this mean? Well, it means we're going to get two products. Hooray. The other thing we want to keep in mind, and I'm pretty sure this is a safe assumption to make, is that of our conjugated system, ultimately, we are going to have a double bond located in between our 2 and our 3, okay? And the other double bonds should be eliminated. So let's keep that in mind. Well, what are we adding to this? Well, we're adding the same thing because the problem didn't say we're changing anything. So our dienophile, and a dienophile is just something with a carbon-carbon double bond. Our dienophile in this case is still going to be this. I don't really like putting the hydrogen in, but there's a hydrogen there. Okay, is this symmetrical? No. All right, so we need to do some resonance stuff here. Because there's no symmetry, we need to see if we can get some charges on things. So let's start with this one. What can we do? Well, we know oxygen is very electronegative, and we know that oxygen, 6, 5, 4, 3, 2, 1, 0, is going to have two lone pairs here. So we're going to get rid of one of those lone pairs. Let me keep that. This is going to resonance contribute. We're going to hop up one of these pi electrons to our oxygen, give it a full octet here, 6, 5, 4, 3, 2, 1, 0, but it's giving it a negative charge, okay? And because this goes here, this follows. Ring around the rosy, and boom goes the dynamite, okay? But don't forget, there's a positive charge here because there are two hydrogens here, which are still here. We have a carbon, which likes to be at 4, 3, 2, 1. We still have a +1 charge, okay? So this is our resonance contributor here. Now, remember that with Diels Alder, we want to do our conjugated diene, and our dienophile. We want a negative on our conjugated diene. So this is our second one. This is our dienophile. So we want to look at where our positive charge is. So this is extremely important. That's where we're going to make our connection. Now we need to make a negative charge in our original conjugated diene, okay? And our conjugated diene is up here. Well, what can we do? This is 6, 5, 4. 6, 5, 4, 3, 2, 1, 0. Okay, what can happen here? Remember, oxygen is electronegative. So we can do a couple of things here. This is where things get a little crazy. This is where things get a little confusing. In this case, oxygen is going to form a double bond. We're going to send a lone pair somewhere, okay? You don't want to be tempted to like put a double bond here, because then it stops. Like that's not resonance. You're not really doing anything in that case. All right. When we were here, we put a double bond right onto an oxygen. There is no double bond here. So we're going in this direction. Okay. I know it's confusing. So let's map this out. We're going to go in this direction. We're going to form a double bond there, and it's going to push another double bond somewhere else, and that's going to end up moving this. So this is going to resonate to this. So this forms a double bond. This one kicks. Remember, there were two hydrogens there, and they're still there. They're still there. But now we have a lone pair chilling on this carbon. 4, 3, 2, 1, 0, -1. We just formed a negative charge on a carbon. That's a carb anion, right? Dear God, am I doing this correctly? Okay. Let's just take a look at this for a second. And that's good because we created a negative charge on our carb anion. Do we have a positive charge that we just created? 6, 5, 4, 3, 2, 1. Yeah, we sure do. Here, okay? All right. So, and remember, these are resonance contributors because same amount of atoms, electrons, everything. This is still a neutral charge. This is a neutral charge. This is a neutral charge. This is a neutral charge. That's why these are the identical compounds. They're resonance contributors, all right? This is just a better way to draw it. But in this case, we need to resonate because we need a charge to make a preferred major product. Okay, so what in God's name do we do next? Well, now we need to make our approach, okay? So this is what, remember this, positive charge of our dienophile is going to react with our conjugated system of our negative charge. So that is what's going to happen here. So I always like to start with my original conjugated thing, my conjugated diene, all right? So let's see if we can actually figure out what's happening here. So we have this, 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 okay? We're bringing in our positive charge, and we're bringing it in, but as we bring it in, the positive and the negative, if the negative is up here, the positive is going to be like if this is our negative, this is where we want to approach from. But we can switch this. So I think I just need to turn this around. And remember, listen, at the end of the day, we know it's looking like this. We know we're making a ring. All right, we can cheat. We know we're making a ring. okay? And if this was our negative and we're going to put star to star, we just have to kind of work backwards here, all right? We had one carbon, and then we had a double bond, which we're just going to get rid of. But we have a carbon, and attached to this carbon is this oxygen that was on this group. And that was it. That wasn't like a methyl or anything. And what kind of happens here when you merge everything, because remember, this still had like a positive charge, you just undo what you did. You just get rid of all your extra stuff, right? Get rid of your charges. You put your double bonds back where they came from, right? So when you move this in, just get rid of that double bond. Just put it back where it came from. Neutralize the negative charge that was here. Just put the double bond back where it came from. Neutralize this positive charge that was on this methoxy group, okay? This should be the answer to this question. So bringing this in, carbon. I feel like it's not. I feel like I'm missing a carbon in here somewhere. We know we're making a ring. I think because my original thing was an O with a C and a C and a C, 1, 2, 3, I think my answer is one carbon extra. I think it's this. That's what I think my answer is. Let's check Slater and Chegg and see how I did. This is 40 on 358. All right, Slater's up first. Close. They have a double bond on an oxygen. Why do they have a double bond on an oxygen? Oh, because we weren't getting rid of our double bond. We were putting it back where it came from. And in this case, I said it, I just didn't fully do it. This double bond sits back where it was, which is here, right? We're just putting it back where it came from. And I feel like this is going to go here, and this goes here. I guess that's what neutralizes the charge. But there's not another double bond. This is like nuts. But that's it. This is the answer. So we connected everything correctly. We just forgot to put the double bond back. Let's check. Chegg. 39. $40, yeah, gives us the same thing. It just flips the oxygen, but that doesn't matter. Oh, God. Well, there it is.